Hello guys, my name is IBM and this is going to be Dynamics lesson 2. I think this is going to be lesson 2. In lesson 2 we shall basically concentrate on solving problems involving Newton's laws, especially the second law and maybe the third law. And this is going to be the major concern in lesson 2. So let's begin with what we mean by a balanced and unbalanced forces. So we shall always need to draw what we shall call a free body diagram in solving problems involving Newton's laws. So in handling problems involving Newton's laws, start by drawing a general sketch of the situation. Of course, in the Cambridge exams, many times the sketch is given, but in other curriculum, you may find that the sketch is not given. So on the sketch, you're supposed to show all the forces acting on the body, both the known forces and the unknown forces with arrows, which arrows represent the forces in approximately the correct direction and approximately to scale. Then if you should label each force with its magnitude or with a symbol if you don't know the magnitude. For example, you could use W for weight, T for tension, and so on and so forth. So for each force, you must know the cause of the force. For example, it could be due to gravity, that is the weight. It could be friction, and you must also know on what object the force acts and by what object it is exerted. So if it is a friction, you know that is between the two surfaces in contact. So the label diagram is what we are going. The label diagram with only the forces acting on the body is what we shall call a free body diagram. So we shall always need a free body diagram in order to solve problems involving Newton's laws. And a free body diagram shows all the forces acting on the body. And you should also recall that we shall be using F equals ma, especially that is Newton's second law. But every time we use F equals ma, you must be very sure that F is the net or the resultant force. I think when I say net resultant force is just a repetition because net force means resultant force. So in any system of bodies in equilibrium, it means they are either at rest or they are moving with a uniform speed or constant speed in a straight line. That is in accordance to Newton's first law. So in that case, the resultant force is going to be zero. So the acceleration is going to be zero. So when you say the body is in equilibrium, of course, it means it is either at rest or it is moving at a constant speed. And in both cases, the resultant force is zero. And if the resultant force is zero, the acceleration is also going to be zero. And we say forces acting on the body in opposite directions are balanced and they are actually going to be cancelling out each other in that case. So if the system is at rest, or if the body is at rest, or it is moving with a uniform velocity in a straight line, or with a uniform speed in a straight line, the resultant force is zero. In that case, the acceleration is zero. In that case, so if the body acted upon by these two forces, if the body is acted upon by forces and the resultant force is zero, or the forces acting on the body are in opposite directions and they are balanced and they cancel out each other, we say that the body is actually in equilibrium. So in other words, where there is no equilibrium, the object is expected to accelerate or to decelerate to that effect. Where there is no equilibrium, we expect the body or the object to accelerate or to decelerate. And the resultant force is not going to be zero. So in that case, we would say the forces are said to be unbalanced. If there is no equilibrium, the forces are going to be said to be unbalanced in that case. And the acceleration is not going to be zero because the resultant force is not going to be zero. The direction of the acceleration is going to be the direction of the resultant force because according to Newton's second law, if the mass is constant, the acceleration is directly proportional to the force, and the acceleration is always in the same direction as the resultant force. The acceleration is directly proportional to the net force, and the acceleration is always in the same direction as the resultant force. One important thing you need to note is that the speed increases with the net resultant force. Speed increases when the net resultant force is in the direction of motion. So if the resultant force is to the left and the motion is to the left, the speed of a body increases. However, if the resultant force is in the opposite direction to the motion, then we expect that the speed is going to decrease. So a body slows down when the resultant force is in the opposite direction to motion. For instance, imagine throwing imagine throwing an object imagine throwing an object from a given height to the ground. So let us imagine throwing an object or releasing an object from a given height to the ground. So this object has a weight W, which W is equal to mg. So initially, the only force acting on the object is the weight. But as the object falls, the air resistance increases. So the force due to air resistance increases in the opposite direction. So the motion, the net resultant force is going to be downwards initially, because initially the force due to air resistance is in the opposite direction, and the motion towards the ground. So the speed is going to be increasing because the motion is downwards, and the resultant force is also downwards because the weight is greater than the air resistance initially. So in this case, the objective speed is going to be increasing because the resultant force is downwards and the motion is also downwards because the air resistance is still small. So in that case, the speed increases. So we say the acceleration is increasing. The body is accelerating. So if the resultant force is in the same direction as the motion, the body speeds up or the speed increases. If the same object was thrown vertically upwards instead, consider the object thrown upwards. In that case, that means motion is upwards. But remember, the weight must act vertically downwards. In this case, also the air resistance is going to be downwards if the motion is upwards. So, because when it is in air, the forces acting are the forces due to gravity and the weight which are acting downwards. It means the resultant force when the motion is upwards is the weight plus the force due to air resistance which are acting downwards. So the resultant force is downwards, but the motion is upwards. So this body is going to be decelerating because the resultant force, remember the resultant force and the acceleration are in the same direction. But this time the motion is upwards, yet the resultant force is downwards and the acceleration is downwards. So that means when it is going upwards, it is actually decelerating. So the acceleration is instead going to be called a deceleration, which will be negative acceleration because the resultant force and thus the acceleration are in the opposite direction to motion. So if the same object is thrown vertically upwards and the net resultant force is then downwards, the speed is going to decrease. So the body is said to decelerate. So we normally use positive and negative numbers to show the direction of the force, velocity and acceleration, because these are vector quantities: force, velocity and acceleration. So a common choice of these quantities is positive when they point to the right, or positive when they point upwards, or positive if initial motion is downward. So we just look at the initial direction of motion of the body to choose whether it is positive or negative. So we normally use positive and negative numbers to show the direction of the force, velocity and acceleration. Whichever case you are dealing with, just remember that forces are vectors, acceleration is a vector, and velocity is also a vector. You'll at times have to resolve forces into two components at right angles and then apply the second law to each set of components separately. So sometimes you may need to resolve the components of forces or to find the components of the forces, because force is a vector quantity, and then you may be forced to apply Newton's second law either on the horizontal component or on the vertical component, depending on the orientation of the components of the forces. So what the takeaway from this is that whenever the motion of the body is in the same direction as the resultant force, the body speeds up. We say it accelerates. The acceleration is positive in that case. Whenever the motion of the body is in the opposite direction to the resultant force, the body slows down. Therefore, uh, the acceleration in that case is going to be negative, and we call that a deceleration. That's why when you throw an object upwards, its speed decreases to zero at the highest point. So because the acceleration is negative, it is actually a deceleration in that case. So every time you are solving problems involving Newton's laws, you should have this in mind at every stage. Okay, so let's explore more examples for us to gain more understanding and more confidence with Newton's laws of motion. So here I have given, we're going to think about using force vectors to find resultant of vectors, but you must have done this under unit called force, density, and pressure. You must have done this in the first unit of physical quantities and units. So the vector sum of all the forces on a body gives a net or resultant force, or net or resultant forces. To see the vector sum of the forces, we normally add the vectors together, nose to tail or head to tail. For example, consider four forces acting on a mass as shown in the figure below. We have 4 newtons upwards, 4 newtons downwards, 3 newtons to the left, 3 newtons to the right. So we join these vectors head to tail, and if they form a perfectly closed triangle, we say that the resultant of these forces is zero, or the resultant of these vectors is zero. So the body is the forces are said to be balanced. Therefore, if I join the vectors head to tail, I fix this. On it, I add 3 newtons. On 3 newtons, I add 4 newtons. On 4 newtons, I add 3 newtons. Without changing the length of the lines representing the magnitude, if these vectors are joined and they form a perfectly closed object, then it means they are forming what we call, they're acting on an object which is under equilibrium, because there is no resultant in that case if they form a closed shape. In many cases, for examination purposes, we shall only have two forces. We shall only have three forces which form a closed triangle, but these are four and they are forming a closed rectangle. Therefore, there is no net or there is no resultant force on the mass, and we say the forces are balanced in that case. We could find the resultant in the vertical to be zero and the resultant in the horizontal to also be zero. Therefore, these forces are acting on a body which is in equilibrium. Those are the balanced forces. Then let's also briefly talk about the unbalanced forces. So in other cases where there is no equilibrium, the object accelerates. In other words, it speeds up. Where there is no equilibrium, the object also speeds up. In that case, the resultant force is not going to be zero. So there will be an acceleration, which is not zero. And we have just said that the direction of the acceleration is the direction of the resultant force. That is in accordance to Newton's second law, that F equals to ma, and F and a are always in the same direction. So the force and the acceleration are always in the same direction. So the speed, like I've said, the speed increases if the resultant force is in the same direction or is in the direction of the motion, and the speed decreases when the net force or the resultant force is in the opposite direction to motion. So motion and resultant force same direction, that is going to cause speeding up. Motion and resultant force in opposite directions have what we call slowing down. And I gave a simple example that if an object is thrown upwards, the force is downwards. That is, the resultant force is the force due to gravity, which is downwards. So its speed decreases. And on the other hand, if the object is thrown downwards, the force is still downwards. So the speed is expected to increase. So if the force or resultant force and motion are in the same direction, the body speeds up. If the resultant force and the motion are in opposite directions, the body is expected to slow down. Okay, let's do some further examples then. A body of mass 5 kilograms is pulled. A body of mass 5 kilograms is pulled along a horizontal floor by a force P of 25 newtons, applied at an angle of 20 degrees to the horizontal as shown in the figure below. A friction force of 20 newtons acts parallel to the floor. Calculate the acceleration of the box. Okay, so I can sketch the diagram for this just for the sake of making it visible to some people who may not know how to sketch this. And remember, I said when you are dealing with Newton's Newton's laws of motion, or you are solving problems of Newton's laws of motion, sometimes the diagram may be necessary. And we said we shall call that diagram a free body diagram, which just indicates the forces acting on the body. So I'll try to sketch a free body diagram, even when I'm very sure that in the Cambridge exams, most of the diagrams are sketched for you. So let that be the surface, and let's consider a box resting on the surface. Of course, which forces act? The weight of the box acts vertically downwards. Then the normal reaction from the surface is acting vertically upwards. Then it is pulled along a horizontal floor by a force P of 25 newtons applied at an angle of 20 degrees to the horizontal. So let's say the force is applied here, and this force is 25 newtons, and it is applied at an angle of 20 degrees to the horizontal line. A friction force of 20 newtons acts parallel to the floor. So there is friction. I will change the color to show friction. Friction is between the object and the surface. So there is friction, and this friction is 20 newtons. So we want to calculate the acceleration of the box. So to calculate the acceleration, we must find the resultant force, because we can't find the acceleration without the resultant force. So in this case, like I said, you must be recalling your resolving principles or your resolving ideas. So we need to find the resultant. We can resolve this in the vertical. In the vertical, this will be 25 sine of 20. And in the horizontal, the force acting in the horizontal is going to be 25 cos of 20. And for equilibrium, there should be no resultant force in the vertical, but since there's an acceleration in the horizontal, the body is just being pulled along a horizontal surface. So in the vertical, the resultant should be equal to 0. So in the vertical, we have that the weight W, which is vertically downwards, should be equal to R plus 25 sine of 20. Because W is acting downwards and R plus 25 sine of 20 is acting upwards. So this would give us R. But in the horizontal, there's an acceleration, which is most likely going to be in this direction here. So it means the resultant force F, which is the mass times acceleration, should be equal to the force acting in the horizontal is 25 cos of 20 minus the frictional force, which is 20. So I can press my calculator here. The resultant, the mass is 5, so I'll say 5 times A equals to 25 cos of 20 minus 20. And I will divide both sides by 5, both sides by 5. So the acceleration is going to be 25 cos of 20 minus 20. So this is 3.49 divided by 5. So the acceleration is 0.70. So the acceleration is going to be 0.70 meters per second squared. So this is going to be the acceleration of the box. If I wanted to find a normal reaction R, I would still find a normal reaction R, where weight is mg is equal to R plus 25 sine of 20. So R would be equal to mg, which is 5 times 9.81, then minus 25 sine of 20. So that is 5 times 9.81 minus 25 sine of 20. So R would be equal to 40.5 newtons if I wanted to find R. So the concepts of resolving are very important in all levels, especially when you are dealing with the physics. Of course, if you are doing math, you will need this in mechanics, paper 4, I think. You may need some of these concepts in math. Example 2, a person gardening pushes a lawnmower of mass 18 kilograms at a constant speed. So if it is at a constant speed, it means acceleration is going to be 0. Resultant force must be 0 if the speed is constant. To do this requires a force of 80 newtons directly along the handle. So there's a force of 80 newtons directly along the handle, which is at an angle of 40 degrees to the horizontal. Calculate the horizontal retarding frictional force. So I have to resolve 80 newtons in the horizontal. This will be acting in this direction. So 80 in the horizontal is going to be 80 cos of 40. And it will point to the left-hand side. And remember, it is at a constant speed. So the resultant force, which is equal to mass times acceleration, should be equal to 0. And 80 cos 40 is acting to the left, and the frictional force is acting to the right. So I will say the resultant force, of course, is supposed to be 80 cos of 40 minus the frictional force. And because F is 0, so it means the frictional force is going to be 80 cos of 40. When I press my calculator here, 80 cos of 40, this would give us 61 newtons. So that would be the horizontal retarding force or frictional force, and it acts to the right hand side. If the retarding force were constant, what force applied along the handle would accelerate the mower from rest? 1.2 meters per second in 2 seconds. So from rest, it means initial velocity is 0. Then from rest to, I think this is supposed from rest to 1.2 meters per second. So it is from rest to 1 point. So this is going to be v, and time is 2.0 seconds. So what force applied along the handle would accelerate the mower from rest to 1.2 meters per second in 2.0 seconds? Okay. So there are several ways of doing this, but the simplest would be if the acceleration is constant, then I could use, of course, if the retarding force is constant, it means the friction is constant, and therefore it also means the resultant force is going to be constant. So we are going to leave the retarding force to be 61 newtons, as we have already found it. So I'm going to find the acceleration first. So using v equals to u plus at, we want the velocity to be 1.2, initial is 0, and this is plus acceleration, which we don't know, and the time is 2.0 seconds. So it means the acceleration is going to be 1.2 divided by 2, which is going to be equal to 0.6 meters per second squared. So that is the acceleration in that case. Remember, I'm answering part B. This was part A. So that is the acceleration, and the question is what force applied along the handle? The force is applied along the handle. So let's first find the resultant force. But remember, the resultant force F is equal to, let me call that force P. I will just call that force P. The resultant force is going to be equal to, this force will be P cos of 40 to the left minus frictional force. So it will be P cos of 40 minus the frictional force. That should be the resultant force. But of course, the resultant force is mass times acceleration. So we shall say MA should be equal to P cos of 40 minus the friction, which is 61. And remember, the acceleration is 0.6 and the mass is 18. So I'll say 18 times 0.6 should be equal to P cos of 40 minus 61. So I'm just making P the subject. So P will be 18 times 0.6 plus 61 divided by cos of 40. I'll just press my calculator. P will be 18 times 0.6 plus 61 divided by cos of 40. And this is 94. So P will be equal to 94 newtons. Okay, so you'll be finding many questions of that nature in your mechanics of mathematics. Example next, if you take this, a large stone and a small stone are dropped from the top of a tall building. Which one will reach the ground first? So there are two ways of thinking about this. Of course, a layman will think that the large stone is expected to reach the ground first. But if we assume that there is no air resistance, a large object and a small object would arrive on the ground at the same time. Reason: each object initially, before they start, if they start from the same level, let me assume they are starting from the same level, a large stone and a small one, it means their initial velocity is initially 0. And the acceleration for each, if there is no air resistance, is going to be g, which is 9.81, which means their speed after 1 second is going to be 9.81 meters per second. Their speed after 2 seconds is going to be 2 times 9.81 meters per second. Their speed after 3 seconds is going to be 9.81 times 3 meters per second. That means the speed with which they reach here is going to be the same in the first place. Secondly, because in equal time intervals their speed is the same, they will automatically cover the same distance, and therefore they are going to arrive at the same time. So if there is no air resistance, the value of g of acceleration is constant. It doesn't depend on the mass of each of them. So a small stone and a big stone will arrive at the same time if there is no air resistance, because their acceleration is not dependent on their masses. So they will reach at the same time. So if air resistance is negligible, if air resistance is considered, it is the large one to arrive first. Its weight is greater, so it reaches a greater speed before air resistance is sufficient to equal its weight. That is if air resistance is considered. But I'm saying if air resistance is not considered, if if air resistance is negligible, if air resistance is negligible, acceleration is constant and not dependent on the mass. So they reach at the same time. In case air resistance is negligible, then it means the acceleration due to gravity, the acceleration is going to be constant. It will not depend on their masses. Therefore, they will arrive at the same time. Okay. So skydivers jump from a plane. Skydivers jump from a plane at intervals of a few seconds. If two divers wish to jump up as they fall, the second must catch up with the first one. The second must catch up with the first. Part A. If one diver is more massive than the other, which should jump first? Use the idea of terminal velocity. Okay, so if remember they must catch up with the first. If one diver is more massive than the other, it means the one who is more massive will gain a terminal velocity in a very short period of time, therefore must jump later. The lighter one, um, the lighter one, the lighter one has a lower terminal velocity. So the question is, if one diver is more massive than the other, which should jump faster? So the lighter one, or the one with the smaller weight, should jump faster in this case because he has a lower terminal velocity. They will reach terminal velocity in a very short period of time. So they must jump fast so that they cover up a large distance before the one who is more massive, because the one who is more massive will travel longer distance before reaching terminal velocity because terminal velocity also depends on the weight of the object. Therefore, the one who is lighter, the lighter one should jump faster. Use the idea of terminal velocity to explain your answer. The lighter one, smaller, it has a smaller weight, therefore has a lower terminal velocity. So the lighter one should jump fast so that some time is allowed for them to reach their terminal velocity after covering a long distance, because the heavier one will gain its speed very rapidly in a very short period of time. Therefore, for them, they have higher terminal velocity. Then part B, if both divers are actually massive, let's say they have the same mass, suggest what the second might do to catch up with the first. So they say the skydivers jump from a plane at intervals of a few seconds. If two divers wish to join up as they fall, they want to meet as they fall, the second must catch up with the first. If both divers have the same mass, they are actually massive. Suggest what the second might do to catch up with the first. So if the first jumped earlier and they have the same mass, then the second diver must find mechanisms of reducing their surface area so that their speed increases very rapidly. For example, turning the head first and pulling in their arms and legs so that they have a streamlined shape to reduce air resistance or to reduce friction. They are thereby increasing their speed very fast so that they catch up with the first diver. So the option for this could be turn head first and pull in his arms and legs to produce a streamlined shape so as to reduce friction. That is one way of ensuring that the second diver can now catch up with the first diver, because if it streamlines the body, it means the air resistance is decreased or the effect of air resistance is reduced, and therefore can gain speed very fast or can have a higher acceleration to catch up with the first diver. Okay. Here is a simple self-check where I will give a hint. A car of mass 500 kilograms is traveling along a flat road. The forward force provided between the car tires and the road is 300 newtons, and the air resistance is 200 newtons. Cut to the acceleration. So remember I said every time you use F equals to ma, F must be the resultant force. And since this is the force provided by the engine, the forward force, and this is the resistive force, so it means the resultant force is going to be 100 minus 200. So that would be, 300 minus 200 is the resultant force, and is going to be 500 times A. So which I think it gives us A as 0.2. Luke drops 5 kilogram ball, weight 50 newtons, off the roof of his house into a swimming pool below. Upon encountering the pool, the ball encounters a 50.0 Newton upwards resistance force. Upon encountering the pool, there is a 50.0 Newton upward resistive force just upon encountering the pool. Which one of the velocity time graphs best describes the motion of the ball? So it means, first of all, the speed must be increasing before encountering the pool. So it means C is going to be automatically wrong because C is showing that the speed is constant before encountering the pool. So we have to choose between A and B. A is showing that the speed is decreasing before encountering the pool. If air resistance is negligible before encountering the pool, then A would be wrong because we expect that the speed must increase before encountering the pool. At the point of encountering the pool, the upward force from the water is equal to the weight. So at this point, the acceleration becomes zero, the resultant force becomes zero, the velocity becomes constant. So we expect that the last part of the graph should be a horizontal line. So the answer will be B. Now someone will say, but the line is below the x-axis. As long as the line moves away from the x-axis, it means the velocity is increasing, although it may be increasing in an unexpected direction. So here this is an increase in velocity in the negative direction, and then the velocity becomes constant at the point where it encounters the pool. That means the resultant force becomes zero in that case. So the answer would be B. The force on this mass are balanced. The forces on this mass are balanced. We can determine the resultant force by adding the vectors together, nose to tail. So these are three vectors, and I said we can find the resultant by joining them head to tail or nose to tail. And if we join them and we form a closed triangle, they are balanced. If we join them and the triangle is not closed, there is a balance. So let's see. In this case, when I join 8 newtons to 3 newtons to 4 newtons, there is a gap left out. So that means the three forces are acting on a body and there's a resultant. And this resultant could be obtained either by Pythagoras theorem or this could be obtained to scale. So if we try to draw these vectors, we can combine 8 newtons with the 4 newtons. So the resultant of 8 and 4 newtons is going to be a vector of 4 newtons upwards. Then we have 3 newtons, which can be a vector in the horizontal of 3 newtons. So there must be a resultant which should be in that direction. And this is right angled, so we can use Pythagoras theorem. And from Pythagoras theorem, 4 squared plus 3 squared is going to give us r squared. And if we want to find the angle the resultant makes with any of the forces, for example, with the horizontal or with the vertical, then we can use still trigonometry. Students often have coffee and have tea or apple juice. So if I want to find the theta, this is opposite and that is adjacent, so that would be tan. Tan theta is equal to the opposite divided by the adjacent. So I think this gives us theta as 53. If we want to find the resultant in terms of the angle it makes with the vertical, I'll call this alpha. So still have opposite of adjacent, but this time the angles will change. I mean the sides will change. Tan alpha would be 3 divided by 4, which of course would be a 90 or 180 or 90 minus 53, which is, I think that is going to be 30. Alpha will be 37 degrees approximately. Of course, we saw in the unit called force, density, and pressure, you could do this to scale. Alternatively, we have also seen under the first unit of physical quantities and units that you could find the resultant from a scale diagram or from trigonometry and so on and so forth. Yeah, there is a resultant force of 5 newtons at a direction of 53 degrees from the horizontal. This is how we write the resultant. Let me rub off this so people can see this. Because the force is a vector, the resultant force is 5 newtons at a direction of 53 degrees from the horizontal. So that is if we find the angle with the horizontal. We could also state the same with the vertical, which would be 37, 5 newtons at the direction of 37 degrees from the vertical, or with the vertical. A car and a caravan, 5,000 kilograms, are accelerating at 0.5 meters per second. They are moving as a single body with that acceleration of 0.5 meters per second. Find part A, the driving force produced by the engine. Driving force. Of course, the driving force produced by the engine. So the driving force produced by the engine, I'll call this FD. The driving force produced by the engine, I'll call that FD. And if there is no friction, then the driving force is going to be the resultant force, which is mass times acceleration. So the driving force is going to be mass times acceleration. So we have this as 3. This one is 3,000. The other one is 5,000. So the total mass is 8,000. So the driving force will be total mass times the acceleration. Since there is no friction, there is no resistance, the driving force must be the engine must accelerate both the car and the caravan. So the driving force is actually the resultant force here because there is no resistance. In that case, we have not considered any resistance in that case. Then find the tension in, we want to find the tension in the tow bar if there is tension then. So if there is tension, then let's consider the forces acting here. We have already found in the previous example the driving force to be 4,000 newtons. So there must be tension here, or there must be tension in the tow bar. So the tow bar here must be accelerating the caravan only. The tow bar must be accelerating the caravan. I mean, the tension must be accelerating the caravan only, or the tow bar must be accelerating the caravan only. So there must be tension here. And since this is 5,000 newtons, and the acceleration, remember the acceleration is 0.5, so it means the tension here must be accelerating the caravan only. It must be the resultant force on the caravan, which will be MA, where the mass is 5,000 and the acceleration is 0.5. So the tension we're talking about here is going to be the mass of the caravan times the acceleration of the caravan, which is going to be 2,500 newtons. That will be the tension in the tow bar. Then find the resultant force on the car, on the car alone. Of course, we have seen the force which is accelerating the caravan, and we have seen the resultant force of the whole system. Then the resultant force of the car alone must be the driving force minus the tension. So this is going to be the driving force minus the tension, or I can multiply the mass of the car times the acceleration, which will be 3000 times 0.5. That is the force, the resultant force on the car alone. So because there is tension in the opposite direction, that is trying to pull or prevent the car from moving forward as a result of pulling the caravan, then it means the resultant force on the car is going to be the difference between the driving force minus the tension. Okay. So alternatively, math students may use a simpler and more, but still more complex method. For example, there is tension somewhere here. I'll call this one T. So the tension there, if I use Newton's second on the car alone, I would say the driving force is 4,000 minus the tension. I'm looking at the car is the resultant force on the car, where this is going to be the mass of the car, that is 3,000, 3,000 times the acceleration, which is 0.5. Then also I could say for the caravan alone, the resultant force is going to be 5,000 times the acceleration, which is 0.5, should be equal to the tension, because the only force acting on the caravan is the tension. The driving force is attached to the car, even though it is pulling the whole system. So I know the tension from there, and if I know the tension from the second equation, then I can use it for everything else. So if I want to find the resultant force on the car, I can either take the left-hand side, or I can get 4,000 minus the tension. Those are two options. Sometimes or many times the acceleration will not be given, as we shall see later on. So that's how we find the force on the car alone, or the resultant force on the car. I've given a self-check for people to practice. I may give a hint. A car of mass 800 kilograms accelerates uniformly. That means the acceleration is constant along a straight line from rest, which means initial velocity is 0 to a speed of 12 meters per second in a time of 50 seconds. Calculate A. A is the acceleration. Of course, for acceleration, final velocity minus initial velocity divided by t. So that would be 12 minus 0 divided by 50. The acceleration would be 12 divided by 50. The acceleration is 0.24 meters per second. Then the force on the car that produces this acceleration. So the force is equal to mass times acceleration, which will be 800 times 0.24. So this would be 192 newtons. And then the ratio of the accelerating force to the weight. So the ratio of the accelerating force to the weight, so the ratio is simply going to be the accelerating force is 192 divided by the weight. The weight is mg, divided by m, which is 800 times 9.81. So that divided by 800 times 9.81. So this ratio is going to be 0.024. There is no unit. A bullet of mass 0.02 kilograms traveling at a speed of 120 meters per second hits a tree and penetrated a distance of 55 millimeters into the tree. Calculate the deceleration of the bullet. The impact force. So if it decelerates to 55 millimeters and then stops, I will change this to meters first. 55 divided by 1,000. So this one is 0.055 meters. That is v. That is the distance through which it moves. Final velocity is going to be 0. because when it penetrates, it stops after 55 millimeters. And this is going to be the initial velocity. So you have two options. You can use a v squared equals to u squared plus 2as, assuming the acceleration is constant or the deceleration is constant. So final velocity is 0 squared equals to 120 squared plus 2 times the acceleration times 0.055. So it means the deceleration A is going to be equal to negative 120 squared divided by 2 times 0.055. The negative, I've taken 120 to the left-hand side. So 120 squared divided by 2 times 0.055. So this is giving me 130,000, but this is negative meters per second squared. I just rounded off to two significant figures, negative 130,000 meters per second squared. Okay, then part B, they say the impact force of the bullet on the tree. So if that is the deceleration, then the impact force is going to be mass times the deceleration. So this is going to be, because the force decreases from the certain value to 0 when if this is the deceleration, this is the force. The decelerating force is going to be 0.002 times 130,000. I ignore the negative. And this is going to be 260 newtons. That is going to be the decelerating force. A car accelerates from rest to 13.5 meters per second in 6 seconds. If it has a mass of 200 kilograms, what is the resultant force acting on the car? So all we need is to find the acceleration again. So the acceleration is going to be the final velocity minus initial velocity divided by t. The final velocity is 13.5 minus 0 divided by the time, which is 6. So that is the acceleration. Then I multiply this by the mass to find the resultant force. So F is ma, which is going to be 2000 times 13.5 over 6. So this is 4,500 newtons. You can also check that. So we are just trying to explore more on Newton's laws. Let's see how to use F equals to ma in most cases. So if we have two objects joined end to end, for example, a car and a caravan, or any carrier in that case. So the resultant force you can consider, like in maths, you can consider the resultant force on each of these objects. So remember, the total driving force pulls both the car and the caravan. So let's consider the car alone. Which forces are acting on the car alone? One, we have the driving force forward, and two, we have the tension to the other side, or the resistance from the caravan, or the pull of the caravan on the car. So that means the resultant force in that case is on the car alone is going to be ma. Of course, ma is the resultant force, which will be Fd minus T. But then, if we consider the trailer, the force on the trailer is due to the tension in the tow bar pulling it forwards. So this force here is the only force acting on the trailer, which is pulling it forward. And this is going to be the resultant force on the trailer. Therefore, M times A, this should be small letter m. Small letter m times A should be equal to the tension. So the resultant force on the trailer is the small mass m, then times the acceleration minus, which is equal to t. Now, the driving force, of course, is going to be the sum of this resultant force here and this one here. So the resultant force Fd is the sum of these, or even if we add up these two equations, we shall have that Ma plus capital M A. Of course, the acceleration is the same because it is a composite body, so the acceleration is the same. So this is going to be Fd minus T plus T. So this cancels out. Therefore, we simply say that Fd is Ma plus Ma. That is the resultant on the car plus the resultant on the trailer. That is the driving force. If there is no any other resistive force in that case. Let's also talk about rocket problems. So here I say the driving force is Ma plus capital Ma. Let's also talk about rocket problems. Think of a rocket which is being launched into space. Of course, the forces which act on the rocket include the engine thrust and maybe the weight of the rocket downwards. So if the rocket has mass m, which forces are therefore acting? So if T is the thrust of the rocket engine when its mass is m and the rocket is moving upwards, its acceleration A is going to be given by the resultant force on the rocket will be the thrust force upwards minus the weight mg. That is, if it is moving upwards, the thrust force is greater than the weight. So in that case, we would simply say T minus mg is going to be equal to the resultant force, which is equal to ma. And therefore, if I make T the subject, T is going to be equal to mg plus ma. So in order for it to move upwards, the engine force should overcome the weight and also give it an acceleration. So it should be big enough to overcome the weight and also give it an acceleration. That is what we mean by this concept here. Okay, so the rocket thrust must therefore overcome the weight of the rocket for the rocket to take off. Otherwise, if they are equal, it may not take off. If it had already taken off and they become equal, it may just continue with its motion, but at a constant speed. But before it takes off, if the forces are equal, then it will not take off in that case. Okay, let's also explore lift problems. You may find questions about lift problems, being in a lift. So if you are in a lift, of course, the lift is moved by cables or wires. Okay, cables in that case. So we expect tension to be in the cable. And then we have weight of the person and the weight of the lift itself, the total weight of the lift and occupants, which is downwards. So we can assume the lift is moving upwards. In that case, the resultant force upwards should be greater than total weight downwards. So the resultant force, if the tension in the cables is T, then the resultant force must be T minus the weight downwards, which is going to be M times G, where mg is the total weight of the occupants. So using upwards as positive gives the resultant force on the lift as F is equal to T minus mg if T is upwards and positive, where T is going to be now the tension in the cable in this case, and m is the total mass of the lift and its occupants. Therefore, if I make T, remember the resultant force is given by ma, so T minus mg is the same as ma. Now there are three conditions for us to think about here. If the lift is moving at a constant speed, of course, it means the acceleration is going to be 0 in that case. So the tension must be equal to mg. If it is moving, that is if it is moving. If it wasn't moving, and T equals to mg, it will not actually leave its position. But if it was moving and then the resultant force becomes zero, or it moves at a constant velocity, then the tension is equal to mg. Suppose the lift is moving upwards and it is speeding up, that is, it is accelerating. The only way it can accelerate is when the tension is equal to the weight of the object of the occupants plus a force plus a resultant force which will cause it to accelerate. In other words, if the lift is moving up and accelerating, then the acceleration A should be greater than zero. Remember, the arrow here is showing that the acceleration is upwards. So if it is moving up and accelerating, then the tension T should be greater than the weight of the occupants plus the acceleration. The tension T should be equal to the weight of the occupants plus the force causing an acceleration. In other words, the tension is going to be greater than mg because it has a component which is ma. If the lift is moving up but it is slowing down, the lift is moving up but it is slowing down. It is only slowing down because the acceleration is in the opposite direction to the motion. That is the only way it can slow down, or the acceleration is going to be negative in that case. So it means the tension is less than the weight of the object. If it is moving up but slowing down, it means the forces, total force downwards is greater than the force upwards. That's why it is slowing down, it is decelerating. So tension T is going to be less than mg in that case. And if the lift is moving down, let's assume it was moving down and accelerating. Of course, if it is moving down and accelerating, the acceleration and the direction of motion are going to be the same. So if the lift is moving down and accelerating, that is, velocity and acceleration are both downwards and therefore negative, assuming upwards was positive. So if it is moving down and accelerating, it means the resultant force and the direction of motion are in the same direction. So the velocity and acceleration are both downwards. That's why it is moving down and accelerating. And therefore, in that case, we would say T would be equal to mg minus ma is going to be less than mg. Now, why is it T equals to mg minus ma? It is moving down. That means the acceleration is downwards. And the motion is also downwards. So it means the resultant force is downwards. So in that case, the resultant force F is going to be mg minus T, which means ma would be equal to mg minus T. In other words, the tension T is going to be equal to mg minus ma in that case. If it is moving downwards, the resultant force is downwards, which means the total forces downwards are greater than the tension upwards. So in that case, this leads us to T equals to mg minus ma. In that case, the tension is less than the weight. So if the lift is moving downwards but slowing down, it means the force upwards is greater than the forces downwards. It is moving downwards but is slowing down. So it means T is still greater than mg. So the resultant force is going to be T minus mg. So it still means T is greater than the weight. That's why it is slowing down while moving down. So in that case, tension is still going to be mg plus ma, but T is going to be less than the weight in that case. So you need to understand these ideas about the lift problems. Then also we have what we call pulley problems. You may find pulley problems, especially in mathematics, those doing maths. Let's consider two masses attached on a pulley, or attached on a string passing over a pulley. So let the large mass be capital M and the small mass be small m. And let the string be hung over a frictionless pulley. So if the system is released, we expect that the large mass is going to lift the smaller mass. As the large mass moves downwards, the smaller mass is expected to move upwards but because they are linked, we expect the acceleration of both to be the same. So if I consider the large mass first, so on the mass capital M, the resultant force, the weight downwards is greater than the tension upwards. So the resultant force here is going to be mg, capital Mg minus T. This is going to be Ma. So the resultant force mg minus T is going to be equal to Ma. But if I consider this one which is moving upwards, it means the tension T is greater than the weight mg. So it means T minus small mass mg is the resultant force. So on mass small m, T minus mg is equal to Ma. And if we try to add the two equations, we add mg minus T equals to Ma and T minus mg equals Ma. When we add the two equations, I think T cancels out. T cancels, you remain with capital Mg minus small mg equals to capital Ma plus Ma. So if we add the two equations, we have mg minus mg equals to that. So from this, we can find our acceleration. So for pulley problems, look at the large mass, find the resultant force. Remember, the acceleration on the other side is the same as the acceleration on this side because they are joined. So it is moving as a system. Okay, let us also briefly talk about sliding down the slope. Of course, we have already done some questions about sliding down the slope in force, density, and pressure, but it doesn't do any harm for us to remind ourselves. So sliding down the slope, we are going to consider a block of mass m sliding down the slope. And we are going to explore the components of all the forces, the component of the force which acts down the slope. We've already got these components. The weight of the body acts vertically downwards. And we say the weight of the body can be broken down into two components. If we consider this angle as 90 degrees, we say this would be 90 minus theta, which would make this angle theta. And if I resolve mg perpendicular in this direction to be mg cos of theta, elsewhere it will be mg sine theta. So it means the force acting, or the force which is going to move the object along the plane or contribute to the motion along the plane is just mg sine theta. So if there is friction, of course, friction will always act in the opposite direction to motion. So if the object tends to slide downwards, then the friction is going to be upwards. And if it is sliding downwards with a uniform acceleration, then the resultant force F is the mass times the acceleration, which will be equal to mg sine of theta minus the frictional force. So if there is friction, then the resultant force along the plane will be mg sine theta minus the frictional force, uh, which means that this is going to be the force that is contributing to the acceleration. So the acceleration down the plane would be mg sine of theta minus the frictional force divided by m. So the acceleration here is most likely going to be less than the acceleration due to gravity, because after all, it is already mg sine theta, then minus f naught, or g sine theta minus f naught over m. So the resultant force on the block, F, is going to be mg sine theta minus the friction. Therefore, mg sine theta minus the friction will be equal to ma, and in that case, we can calculate ma as required. So that is how we find, or we use Newton's second law along an inclined plane or sliding down the slope. Let's do one example and we close that. We end lesson 2. A car weighs 10,000 newtons. What is the friction required to hold the car in equilibrium on a slope of 10 degrees elevation? Okay, so I will sketch this, just remind you of the forces. So let this be the car. So that is the car. It weighs 10,000 newtons. So the weight is 10,000 newtons. weight acts vertically downwards. The angle of elevation is 10 degrees to the horizontal. So the forces acting on this car we have are the normal reaction force that acts at 90 degrees to the surface. And of course, this is balanced by the component of the weight in that direction. So this is the reaction. So if this angle is 10, this is 90, this is 90 minus 10. So this angle is supposed to be 10 degrees. So this is 10,000 cos of 10 degrees. So that is, if we resolve the weight parallel to the plane, this would be 10,000 sine of 10 degrees. And there is a friction. Of course, they want us to find the friction required to hold the car in equilibrium. So there must be a frictional force acting vertically upwards. So I'll call this friction Fr. So for equilibrium, the resultant force, which is mass times acceleration, should be equal to 0. So the resultant force, which is equal to 0, should be equal to 10,000 sine of 10 minus the frictional force. So the frictional force is going to be 10,000 sine of 10. So this is giving me 1736.5 or approximately 1700 newtons. Okay, so this lesson was basically concentrating on just us practicing using Newton's laws of motion and trying to gain confidence on how to apply F equals to ma, or how to apply Newton's second law. So see you in lesson 3, where we shall concentrate now on linear momentum and concepts of collision. Until next time, bye bye.